Hi, I'm Rosario Gerhardt. I'm a professor at the Georgia Institute of Technology, and this is the second part of the tutorial entitled, What is Impedance and Dielectric Spectroscopy? So if you were working with devices, a lot of the same features are important, whether the material is conducting or insulating, whether you have porosity or delamination at interface layers, whether you have charge accumulation at interfaces. What is the state of the device? Is it new? Is it during midlife? Or is it post-mortem? Has it, already broken down? Impedance can actually help you understand the differences between those. Do you have tunneling behavior in between two signals or dielectric breakdown? Are there any inadvertent impurities? And sensitivity to moisture or the presence of optical excitation or magnetic excitation can totally change the measurements that you get. Okay, so now I can go into real examples. Here is a fairly recent paper that we published in Journal of Material Science in 2015. This was a collaboration with the Packaging Research Center, and we were looking at FR4 boards, which are basically glass fiber reinforced epoxy. And here's just some images showing the glass fibers longitudinally as well as in cross-section because they are oriented in different directions. And here are some scanning electron microscope images with, some reaction at the corners of the glass face. This is just for beautiful pictures. But what I wanted to point out is if you have a good FR4 board, it should be fully insulating, just like a straight capacitor. But if it has undergone insulation failure, its impedance is going to be flat, like that of a resistor, and many orders of magnitude lower. So what happens is if you take the pristine material or one that has some minimal surface effect, and then you expose it to different levels of humidity, you are going to be changing the impedance. And at sufficiently high impedance, high relative humidity, you are going to see several orders of magnitude decrease in the impedance value. And this is, of course, also mirrored by the phase angle, which I don't have enough time to explain right now. In the case of the insulation failure, changing the humidity does also decrease the magnitude of the impedance, but not as drastically as that of the pristine kind of material. So this is one example that can apply to essentially any kind of device that may be subject to humid conditions or breakage in the package or different situations. I also have mentioned that conducting materials can be subjected to charge accumulation at the contacts because not all electrode materials provide an ohmic contact with whatever you're trying to measure. And so this is just demonstration, a paper we published in 2013 about conducting polyaniline films that form non-ohmic contacts and give rise to some frequency dependence that has nothing to do with the properties of the polyaniline. This is all controlled by the contacts. Likewise, this is a more complicated material, silicon carbide whiskers embedded in alumina, which is aluminum oxide, which is an insulator. And in that case, we actually form Schottky barriers. And the way to get rid of the Schottky barriers is to superimpose a DC bias, and then you can clearly see those barriers disappear in size. And depending on the composition, you have slightly different responses. And again, I don't have time to explain, but this was published in the Journal of the Applied Physics in 2009. So I've given you two examples. I just want to remind you again, this is the nomenclature. And resistors are flat as a function of frequency. Pure resistors, these are ideal resistors. Inductors increase with frequency. Capacitors decrease with frequency. And we only get semicircles in the complex impedance plane if we have RC circuits in parallel or LR circuits in parallel. If they're in series, we saw that they do not form impedance semicircles, but instead they show admittance semicircles. Okay, so I have some data here for orientation of features can actually control properties. And I have two particular examples. The one over here, these are cellulose fibers, like for paper, that were coated with conducting ITO nanoparticles. And the anisotropy of the fibers actually controls what the properties are. In the second case, we have carbon nanotube networks. And when you make measurements in plane, meaning along the length of where the nanotubes are, you can actually see about 10 orders of magnitude difference in the resistance depending on how thick the layers are, whereas if you make a measurement through the thickness of the film, the change is not as drastic. And just to illustrate, I don't have time to explain this in great detail, but depending on how thick the film is, you may see very, very different response associated with the same material because of the way that it is being interconnected. Finally, I want to talk about these very, very tiny ITO conducting nanoparticles. These materials are made as colloidal solutions. And so each of the nanoparticles, which is a perfect little crystal, has a fatty acid coating. And this is what they look like. They're completely clear, except for when they're treated in argon. I don't have really time to explain the details here. You can actually look at for the paper on Journal of Material Science in 2013. But again, this is the same material, just heat treated with different temperatures. And you can again see a change of about 10 orders of magnitude with the same material as we modify the properties of that insulating coating. And so here is the magnitude of the impedance for the samples that were air annealed, and then for those that were argon annealed. And they look similar, but they're not identical. In the argon annealed, the change is not as quick as it is in air, and there are reasons for that. And here are the accompanying phase angle graphs. So the impedance changes by 8 orders of magnitude, same material. One has a very, very thin insulating coating. This coating is less than a nanometer thick. We haven't published that work yet, but we're going to. And the analysis is much more complicated than it appears to be just based on the impedance angle. We've also done lots of work with composite and ceramic matrix composites filled with conducting fillers. And without going through a lot of presentation, I have 2 cases here of 2 samples that were basically made under the same conditions, except in one we had a different temperature than the other. And again, just like in the previous case, you see a very big difference in the position or the composition at which you see the big change. In this case, we don't see formation of inductive behavior, but in this case, we do. And so there is a lot of additional things that can be said. We have published papers in the Journal of the American Ceramic Society, and this is what the samples look like. This is just to summarize the point that when you have a heterogeneous system, it is possible to have many, many different types of interfaces, and we have an explanation for this in the papers listed. The final example that I'm going to give you is the opposite. We start with a polymer, and we're going to add high dielectric constant fillers to increase its dielectric properties. And so this was actually originally done for an IEEE conference back in 2015. And the dark region is PVDF, and the light regions are barium titanate nanoparticles. And we can actually see here that the real permittivity, as you increase the amount of the BT increases, whereas the dielectric loss increases, but not as much as you might expect. So I forgot to mention here, these are simulations from CONSOL showing that as they get closer, there's an interaction between those barium titanate particles. So what we ended up doing is we added, this is a representation of the previous case, we added carbon nanotubes, but at a small amount so that they don't form a percolated network. And this is a beautiful slide to show you the beauty of looking at all the different functions. If you only look at the complex impedance plane, this looks like a very boring, you don't even get a complete semicircle. And you can't see very much from it. However, if that data is converted to permittivity, and we actually do see the differences for 3 different cases. And the loss at a high content of BT ends up getting higher than 0.1. It's approaching 0.25. But then if we convert this data to the AC conductivity, which is the real part of the admittance, we now see all the insulating samples line up very nicely. But if you have too much combination of the barium titanate and the nanotubes, you begin to see an increased AC conductivity. So this is a really great way to actually, kind of figure out what is the ideal composition that will give you the properties that you're looking for. And this was published in 2016. So to summarize then, measurement-dependent factors, I have already mentioned. Equipment specifications are absolutely vital. Some machines are better suited for more insulating samples. Some machines are better suited to more conducting samples. If you are in a different environment, you really have to pay attention. You can't make a measurement in the middle of the summer, even if you are in a pseudo-controlled lab. You still need to keep track of what the humidity is, because if the humidity reaches 45%, I can guarantee you that if you have insulating samples, you are going to get some adsorption, and that is going to affect your measurements. Obviously, frequency and temperature, the electric field orientation, the material, the size and the shape, what is the ratio of the material conductivities and size features, whether it's a material, heterogeneous material or a device, and how are these phases or components connected. All of these things can actually have an effect on the response that you measure. So, in order to summarize here, I want to tell you some of the things I've already mentioned, but this is typical trends that I have observed for the last 35 years. Insulating materials show large frequency-dependent impedance responses, but minimal frequency dependence in the dielectric properties. However, insulating materials are extremely sensitive to moisture. And of course, this is true if they are porous, they are able to pick up water, or they have alkali ions or in contact with alkali ions in some way or another. Impedance spectroscopy is an excellent method to separate these different effects. And one must use, for the issue of water, one must use lower frequencies than the microwave range, because the microwave range only picks up bulk water. It doesn't pick up adsorption water. Conducting materials, in contrast, are more susceptible to being affected by the types of contacts used, and one must be sure to be making ohmic contacts in order to really trust the results that we obtain. So this is just to indicate, dating back to 1800s, we don't have that much data, but it's mostly on dielectric materials. But as you can see, 1950 is when impedance spectroscopy started taking off. And it's the 70s when computers really came about that made it possible for us to do all of the transformations that we can easily do. And even though this doesn't look like a huge increase, the reason it doesn't is that this is a log scale. And so this has only been summarized up to 2015. Of course, when we hit 2020, I expect that to be even higher. So if you are interested in using this technique, the suggested procedure is to establish the most suitable baseline testing setup to obtain the desired response for the materials or devices that you are interested in. And you need to develop master curves for the particular parameters of interest. And then you have to model the response using equivalent circuit and electrical impedance-based microstructural modeling. And this is absolutely vital. You must corroborate the models with complementary experimental characterization techniques to evaluate the changes predicted, because the model can tell you one thing, but you really need to find some other way to ensure that your assignments are correct. And then once you do that, then you can monitor the changes against the predicted changes to develop more detailed long-term models. So I would like to acknowledge continuous research funding from the National Science Foundation, additional funding from the US Department of Energy, NASA and industry, many different small companies who have trusted me with some of their very special materials and devices. I also would like to thank the Goizueta Foundation faculty chair for funding my travel expenses. And of course, the expert series for the I2MTC conference for giving me the opportunity to give this presentation. And here's a picture of a former group. All of these students that are there are all nicely working in different parts of the world. Thank you so much.